things that are happening, years in the past, and then the light travels for years to our eyes. When we talk about galaxies, that's stuff that's happened millions of years in the past, traveling down towards us for millions of years, hitting us now. And we can do that in theory all the way back to the edge of the universe, which is something that we like to do. And this is a kind of little movie taken by Hubble, where Hubble focused on a tiny piece of the night sky. It's not bigger than a grain of sand would be at your arm's length. And then it kept exposing longer and longer. And it took it a little week, where it kind of found the richness of structures in the universe. And the beauty here is really that the longer it exposes, the further back you get to look in the universe's time, and further out in the universe's distance. And this becomes a very rich image as we go towards 10 billion years. It stops after 10, not because there is an edge to our universe, but because that's the edge we can see. And I want to emphasize again, right, this is a thumb held at, 40 meters distance. That's the area that all of these galaxies are exhibiting. A grain of sand at an arm's length, you can put quite a lot of grains of sand around you, and every one of them are filled with this amount of structure. So to turn back to the galaxy that was weird for us, it's 140 million light years away. This is the unit in kilometers, if you're more used to that. It's fairly long. That means that 140 million years ago, two stars merged. They send out this little sound. Then that sound and the light that it emitted traveled from somewhere in the late Jurassic period through the entire Cretaceous period, through the dawn of the T-Rex, through the death of the T-Rex, through the existence of terror birds, and through the next 65 million years of Earth's evolution. And then it hit Earth in 2017, 2 years after we invented the capability to hear the universe. Which is quite nice. When a signal's been traveling 100 million years, it just hits us 2 years after we learn to hear it. That's a lucky fortune. And that means that when I say these little pixels turned on, that wasn't a faint signal. It was the light of 100 million suns that suddenly appeared and suddenly disappeared again. So this is what we think happened. We had two stars, both of them as massive as the sun, but for some reason both of them, smaller than the distance between here and Tokyo Central if you go to the Imperial Palace. So they're not very big, these stars. They have the mass of a sun. They're turning around each other a few hundred times a second. They've all been orbiting for billions of years, but now, as they get closer and closer, they sing a song of time that they're sending out, and the frequency keeps getting higher and higher and higher as they spiral closer and closer towards each other. And then at some point, they're going to merge, and then something weird is going to happen. And in that moment they merge, they're going to do a lot of impressive stuff, and we'll see that something dramatic happens. They light up, and that's the thing we got to see in light. So you hear the sound of the universe, and then you wait a second, and then the light comes to you. Okay, so these are the objects I want to explain to you, and I want to show you why I think they're some of the most beautiful things we have in the universe. To get to them, we have to appreciate why the stars are so weird. So the stars are neutron stars. So this is a sun. It's our sun, actually. It's 700,000 kilometers big. So even if you took the Shinkansen, that'll take quite a few months to get from one side to the other. Now, if the sun right now is in a balance where gravity is pushing it inwards, light from the inside is blowing it up, and in that balance it can stay for billions of years. But at some point, all balances end and the gravity wins and pulls it together, and it'll pull it into an even more and more dense object. Now, things bigger than the sun somehow press towards the very limits of what gravity finds reasonable, and that's when we get these neutron stars. And we get this thing that becomes smaller and smaller and smaller until it becomes, smaller than the center of Tokyo, and then it explodes in a supernova explosion, which we still don't really understand because the laws of physics are quirky. But at its heart, it births this object, which is a neutron star. And one of the things I want to convince you about is one of these objects is super strange. Two of them going around each other is absolutely crazy. Just want to get free of this cable. So, what are these neutron stars? They're the densest objects in the universe. Now, density here, 100 million tons in something a centicube big, so a centimeter in each dimension. 100 million tons, that's a lot. That's a teaspoon of this is more than every person on the planet in weight. A tablespoon and you could take Mount Everest. This is as dense as nuclear matter. It's not to criticize anybody, but we're all really empty on the inside. In the sense that between the atoms, between the nuclei of the atoms, there's a lot of space until the next nucleus exists, until the next thing of structure. And most of us are nothing. But this is stars where you've pressed that space together and you've managed to make a whole star the density of a nucleus, of the center of its orbit. And they have other quirks. They have the strongest magnetic fields in the universe. That's 1,000,000 billion times larger than on Earth. That's 15 zeros. Again, a lot of zeros, but it's a bit hard to relate to. So we can think about what happens to atoms in that structure. So we're kind of used to thinking about the Bohr atom, like the nucleus and electrons going around nicely. But if you have so big magnetic fields, then atoms start to arrange themselves in long filamentary structures or sheets of planes, kind of like Italian spaghetti. And that's what actually astronomers have named it after. So you get the spaghetti phase of atoms and the waffle phase and the lasagna phase, which are the interiors of these stars that are literally a new kind of constellation of matter. Quite different from what we know. And quite delicious. Yes, and so you have these objects here. There's the densest objects in the universe, the strongest magnetic fields, the most precise clocks. They're near the gravitational limits of black holes. And you're going to take two of them, and you're going to throw them at each other. Now, they were orbiting around each other 500 times a second. They're as big as Tokyo, so if you let Tokyo spin around itself 500 times a second, you're moving quite fast. You're moving at around 20% the speed of light, 100,000 kilometers a second. And then you're going to merge them together. And you're going to throw two objects as dense as nuclear matter with the masses of stars and the sizes of Tokyo at each other at mildly relativistic velocities. And what we want to ask is, what happens when we do something like this? Now the first thing, or the most ultimate fate of this, is this kind of nice, beautiful object of I guess, poetry and astrophysics. But that's that most of the matter of these two stars is going to fall into each other in all eternity. Neutron stars are the limits of reason we have in the universe. They're the last bastion of where the laws of physics make sense. If you throw two of them at each other, there is nothing that can beat the gravity of that, and so gravity just wins all the way down. And so the center, the 99% of the masses of these two stars just collapses inwards in all eternity, forming a black hole. And that's kind of fun. You get to see the birth of a black hole. And for the first time actually naked in some sense, because there's nothing around it that shields it. We get to see this was a thing in the universe. We could see them, we could hear them, and a moment later they disappear and they fall away from our part of the universe. So there's the birth of a black hole. I very much like black holes, so I just added a few cool slides about black holes. Here's a black hole, and because I like ray tracing, here's light moving towards a black hole. They do fun stuff. It bends around the gravity of the black hole. You can see there's light here that, normally we're used to thinking of light traveling in straight directions. That's not true with black holes. The gravity of black holes is so immense that they bend the fabric of space-time itself, and light starts making weird shapes. That also means that there are paths of light that can fly around a black hole and back to you. So you could, in theory, see yourself on the edge of a black hole. There are these weird, quirky things. They're beautiful. Here is actually a simulation where you get to see it. This is a ray of light. It gets closer and closer to the black hole. As it does, it bends more and more. And at some point, it's done a full 180 journey. And then it returns back to you. And that means if you're looking along this sideline, you'll see the photons that traveled around the edge of the black hole and back to you. And you get a little distorted image of yourself in kind of mathematical theory. So these are weird objects. They have all kind of quirks of the laws of physics. They have these, weirdly luminous abilities. They can shine, punctures through galaxies. This is a structure much bigger than a galaxy, even though, like, if this is the size of the galaxy, then the size of the black hole is smaller than a bacteria in my finger, but it's still blowing out structures that are bigger than galaxies. And it's blowing out structures. This is our own Milky Way. This is the Milky Way plane. And this is a huge bubble orthogonal to the Milky Way plane that we believe to be from the black hole we're all orbiting around, which is blowing up a storm from the center of the Milky Way. So that was mainly just to communicate that this thing, seeing the formation of these things are kind of fun. You get to challenge the laws of physics, and we get to learn something from it. Now, this is all very esoteric, but it turns out that in this merger, the 99% was the black hole, but the 1% ends up being us. And that's kind of cute. Because it turns out that there are atoms in your body right now, atoms responsible for keeping you alive, and without which you would be very dead, that are produced when these two things merged, and somehow later on they end up in our body. So just to do like I really like the periodic table, so we're going to do a quick crash course on what the periodic table has in it, but from an astrophysicist's point of view. So this is the periodic table. That's hydrogen, that's helium. That's created in the early universe from the Big Bang, from the residual energy of the universe. You form the lightest things, but then you need the story of the universe to go through and make all the richness that is us. And so the first part you do is you form stars. And in stars you can fuse atoms together and you can make heavier things. You can make carbon, oxygen, silicon, all the things up to iron. You can also make some supernovae and then you can blow it out back into the universe. You can also make these giant stars that are about 1,000,000 times bigger than the sun in volume, which churn things together and you form parts of the periodic table. The thing is, there's a huge part of the periodic table that still to this day is debated from where it comes from. And I believe, and it's at least ongoing effort on our research group, to show that these things are made when neutron stars merge. And so these aren't esoteric elements, right? It's stuff like iodide in our bodies right now that is controlling our metabolism. It's stuff like molybdenum. Molybdenum doesn't have a great PR department. We don't know about it. But plants use it to fixate nitrogen, so you should be happy that you have nitrogen in your DNA, and you should be happy that molybdenum exists. It's uranium and thorium. They really don't have a good PR department. But they're also important for the history of the Earth because the Earth is mainly a nuclear reactor in the core, and that heat comes up and gives us a nice molten core. So it's nice that we had these elements that produce stuff that made Earth habitable, that made plants live, that made us live. And there's not a lot of them on Earth because they're rare things to create in the universe, but there's enough of them that we form. And so at least a part of this story ends up in us. Okay. So what I kind of wanted to talk about is the formation of the black hole, this curious thing of neutron stars, and the origin of the heavy elements, and to give you the story of how they're all tied together. Just want to make sure I'm not running over time.
No, you're good.
I'm good? Banger. So we have 20 minutes, and I think we can definitely get through all of this if we have a bit of fun. So my current research is about how this explosion looked. And it's because once we understand how this explosion looked, we get told something about this inert physics that happens when two stars become a black hole, and about the atoms that shape us. And so what people have historically done is they've taken the laws of physics as good as we know them now. Of course, they're somewhat fallible in this context, but we take the laws of physics and we let two stars on a computer simulate the laws of physics. We let them merge, we let them become one thing, we let them collapse to a black hole, and we see what happens. What would happen to the particles, what stuff would be thrown out, what things would be produced, what would the explosion look like. And the fundamental history coming out of all of these laws of physics is that it's very complicated. It's complicated because this is a borderland of the laws of physics, right? Its density is so great that we don't have them anywhere else in the universe. Its gravity is so great that we're on the edge of a black hole. It's particle physics on the edge of things we don't normally ever even interact with. Its magnetic field so strong we don't even have an analog of it in the universe. So they are kind of in this uncomfortable corner space of the laws of physics where we don't know what's supposed to happen, but we've tried very diligently within the best supercomputers in the world to simulate what you'd see. And this is at least some of the suggestions. Now what I do instead though is I try to look at what the data is. What did this explosion look like when we saw it? And this is the colors of the explosion. I forgot to translate that bit. But this is wavelength, and this is intensity, so how much a color is shown. So you can kind of see as you go from the ultraviolet into the infrared. You know, this is blue colors, this is green colors, this is orange colors, and you can start to learn about what is made, or what is the shining when these stars merge. What is the light that we get to see? We can combine that with the sound in a moment. But the one thing is this pattern of light, you've actually all seen it many days of your lives, hopefully. You've experienced it almost every day you've seen the sun, because this is actually also the colors of the sun. This thing shone like the sun, but it was just 100 million times brighter. And that's kind of a bit curious. You can do something fun with how do you get something to shine 100 million times brighter than the sun, but with the same colors. That requires it to be 100 million times bigger. If it's 100 million times bigger, I should say this thing was taken about 30 hours after the two stars merge. It needs to be 100 million times bigger in the night sky. Then you have a time and a size, and from that you can calculate a velocity. And that means these things are expanding at 100,000 kilometers a second, or 30% the speed of light. So now you can measure the stuff that's going on. And you can see that when the two stars merge, the 1%, the little thing of stuff they threw out with huge velocities. So that's one thing that I think is fun. Another thing is the fact that when you see this, there's places where it's not like the sun, where light disappears. And in quantum mechanics, we're very happy about that because everything in the universe, every periodic element we have, right, it has places where it interacts with light. And this is where the lightest element, hydrogen, interacts with light. These are the colors that it would remove. And all elements have their own little signature, and we can go searching for it. Now it turns out that the 38th element in the periodic table, one of these heavy elements, has the ability that it absorbs light right around here, which is where the light disappeared. And now we've gone one step further. We've found that not only is the matter thrown out at these wild velocities, we're actually seeing for the first time the genesis, the synthesis of the heavy elements in the universe. We are seeing that elements from this part of the periodic table are formed in the collision of neutron stars. So when I said it was a debate earlier, where does the heavy elements come from? This is actually the scientific proof that now we can begin to answer it, because we can see the moment the universe started to create these things. That's kind of cool. Here's another one. This one we made last. Yes? Actually, it's 2 years ago. Well, I made this element. Well, the universe made it, and I found it. And you can see that there's this stuff that disappeared. This is the 39th element of the periodic table. And then you can start plugging in and seeing that we're beginning to do this puzzle piece of the periodic table, trying to tie it all together. And the good thing about job security is that we're missing all of these. So we have a fair bit of work ahead of us. But it is this work in progress of trying to see the synthesis of these elements. And to show where they're created in the universe. If we go back to the explosion again now and ask, where are these elements around the explosion? That's a kind of clever question we can ask. Where did they end up around the explosion? Then it actually also tells us the shape of the explosion. So if we do this simulation again, and this time I want to make you focus on what happens after it's bright, and try to notice where all the elements are getting thrown out. So this is our kind of best reconstruction. Given, you're tracing where the elements are getting thrown out, how does this look? It's a lot of complicated physics. Two stars, they're sending out this sound in the universe. They're about to merge. They're about to form a black hole. When they do, where do they throw out the matter? This is what we observe, or an analog of it at least. This kind of nice semi-spherical fireball of heavy elements. And so that is kind of an observational fact based on the data, one that we still don't really understand. We don't understand it because we don't know the laws of physics in its limit. But it's not really the same as those simulations I showed you before. The simulations were complicated, right? There was all these things, stuff could get thrown out when the two stars are falling into each other and thrown out in that plane. But here it's this beautiful spherical fireball of stuff. And honestly, it would be nice if I could tell you why this thing is the way we think it is. We don't. I should also say this is not a consensus, it's a debate in the scientific community. We're literally on the cusp of discussing what are we seeing when we're seeing the universe. So it's not necessarily correct, but we think we're seeing this weird fireball of heavy elements expanding at 100,000 kilometers a second. Now, if you go back to your simulations and you put in the laws of physics and you then ask, what do I have to do to make this explosion as spherical as our observations seem to suggest, then you can start tweaking the laws of physics and figuring out how they're supposed to be in this edge of the universe. And the answer is complicated, but one of the easiest ways to get towards a prettier explosion is if you put a huge energy bomb in the middle of the explosion and you kind of detonate it. And then you let that energy kind of push everything out equally instead of getting this weird complex shape. Now where that energy would come from is quite difficult to answer. We don't know. We're still searching. There is a huge magnetic field associated with these stars, and there isn't supposed to be one associated with a black hole. And maybe the magnetic field does stuff, but we're still trying to solve this. And so that still remains an open question. Now, if this ends up being correct, though, I wanted to show you kind of a long-term goal of mine that I hope we can maybe shed a bit of light on with these neutron star mergers. And that goes back to one of the oldest questions in astrophysics: how old is the universe? And so this is the current model of the universe as we believe it is. It says that there's stuff like us. We're the 5% of the universe. Stuff that's made of atoms like us and the stars and the interstellar dust. That there's much more of the universe that we're not seeing. There's 6 times as much stuff that's interacting in gravity, but seemingly not with light, kind of like black holes. And then there is a whopping 2/3 of the universe that's not only not interacting with light, it's not really doing what gravity is supposed to do. And so we made this model of the universe. It's kind of pretty in some ways, ugly in others, but this is our best understanding of what the universe has done through time. And the nice thing would be if this model could then explain how old the universe is. The truth is we still don't know the age of the universe, and it's actually a bit odd because we made 2 ways to measure the age of the universe and they don't agree at all. And so fundamentally it seems to imply that maybe our whole model of the universe is flawed. Maybe the universe isn't consisting of what we thought it was, maybe it's very different than the laws that Einstein thought of. The 2 measurements come from 2 different edges of the universe. There's one measurement which is taken from a supernovae, like this one. This is the one Tycho Brahe discovered, another nice Dane. So this is supernovae are nice in the sense that they explode. They're luminous. You can see them in faraway places. You can kind of calculate on them, and you can see how far away they are. If you know what galaxy they're in, you can also see that the galaxy is moving away from us, and then you can measure that. That's because the universe is expanding between us and it. And if you roll the clock back, that means you can calculate when everything was at the same place. And that's what we do with supernovae, and they tell us the age of the universe is 12.8 billion years. And they tell us that with an uncertainty of 200 million years, which is actually quite nice. Then there's another measurement of the age of the universe, which comes from the first light we have in the universe. This is called the cosmic microwave background, and it's the stuff that's behind everything else. So if you look out to the night sky, and you look behind the stars and behind the galaxies, behind everything, and you keep looking backwards, then around the whole universe there's a firewall, and it looks like that. It's a firewall because as you go back in time, and as you look further out into the universe gets hotter. At some point it gets hot enough to ionize everything. Everything becomes, a plasma like the surface of the sun, and then you get the surface you're looking on. And that also actually is telling you how big the age of the universe is. It's telling you a lot of structure, but it's saying the age of the universe is 13.8 billion years. And it's telling you with an uncertainty of 100 million years. So now you have 2 measurements of the age of the universe. They're both incredibly precise. They're both like 5 sigma apart from each other, so they disagree with 1 billion years. So kind of according to the rules of statistics, that means that our current model of the universe can't tie the early universe to the present. Somewhere between us and that firewall, the universe kind of breaks in the way we thought it worked. Or alternatively, one of these measurements are wrong. So there's a lot of attempts done different places to see whether we can use these measurements of the universe to develop new measurements of the universe to try to test whether these measurements are correct. And so what's nice about this neutron star merger is that it has a lot of these nice properties. It's quite luminous, it's transient, you can see it far away, you can see it in another galaxy, and you can see that galaxy moving away from us. And so if we try to do it from this little explosion that we had in 2017, we can measure how far away it is. It's about 140 million light years, as I said before, and you can measure how fast that galaxy is moving away from us. If you calculate that, you can get to the age of the universe, and you get 14 billion years plus minus 600 million. Now that's closer to the early estimate, but it's worth keeping in mind that's a big error bar, that's a big uncertainty. So we're not actually quite sure, like, this is one object that's in theory telling us the age of the universe to 5%. It took 2,000 supernovae to get the precision before that was 3 times this. So this is actually a very nice object, and with a few of these you could in theory make a meaningful statement about how quickly the universe is expanding. Okay, so really to end all of this, I guess I wanted to say this explosion is kind of to me a little beautiful Big Bang. And in contrast to the Big Bang, where we only get to see it from the inside and everything around us is kind of this firewall and there's some limit that we can't see past, here we get to study the laws of physics in these weird limits evolving in time. When the two stars merged, they expelled matter moving at 100,000 kilometers per second. The matter was as hot as the universe was 1 second after the Big Bang. It's literally the nucleosynthetic, the conditions to form things like the Big Bang did. But we get to see it and study it in the hours and days that pass. We get to see the genesis, the moment the atoms form, when the electrons sit upon the nucleus forming the light. We get to see that happen live. You get to study this kind of weird putative regime before the black hole forms. Our most recent paper, which is getting submitted this week, no, maybe next week, if I'm a bit lazy, we think we can measure the time the black hole formed to 30 milliseconds. So we can say, at this point, it existed, there was two stars, and 30 milliseconds later, you had a black hole. And we get to study these regimes of the laws of physics really, really quite dramatically. And so it's quite a beautiful thing. Wait, sorry. And I guess it's just to say that all of these things, the genesis of the elements, the age of the universe, the curious explosions of surrounding a black hole, all of that was just those few pixels on the night sky that lit up in August 17th, 2017. It's not a lot. The universe just sent a signal and we caught it at the right time. There are more of these signals traveling towards us right now, and some of them will hit in a year's time and some of them in a decade's time. And as they do, we should kind of watch out to the night sky and see what stories they reveal. With that, thank you all for listening. And if you have any questions, I'd be happy to answer.
Okay, thank you, Albert, for a great talk. So we have time for some questions and answers. So please raise your hand and I'll call on you, and then Albert, you can answer with Mike. So, yeah, over there.
Yeah, thanks for the great talk. Can you remind me of how you use the Ubuntu?
That's a fair question. So it's what you do is you are using that it's luminous, so you can see it far away. Then you need to know how big it is that you get from the elements, and then you need to know how intrinsically luminous it is, because if you know how big it is and intrinsically luminous, you know how luminous it should be. If you compare that to the thing you're observing on Earth, that gives you a distance from the circumference of a sphere. So you have to know the intrinsic luminosity, and that's where it comes in that it's shining like the sun. Because as long as it's shining like the sun, it has the same kind of amount of photons it emits per cubic meter as the sun does. And so you're using the fact that it's a very nice kind of super sun.
So you're using the distance to measure the age of the universe, sort of as in how you're using the supernovas.
Exactly. So is the only thing the kilonova is doing, or the neutron star merger explosion, is you're getting a very nice proxy for how far away this galaxy is. And then you ask, how fast is that galaxy moving away from us? And once you have, a distance and a velocity, you just have to time the clock back to get back to here when that galaxy was where we were. Yeah, that's a good question.
Yes.
How many of these neutron star mergers happen? Is this the only one we've observed?
It's the only one we heard and saw. One happens in every galaxy about 100,000 years. So that's pretty rare. It's not going to happen in the Milky Way anytime soon. But we do look at 1 million galaxies now, right? So the way we're catching them now mostly is through just the light they're sending. The problem with I guess having just the light is that you really want to hear the sound when the two stars come in, because that's telling you exactly how big the stars were and their properties. And so that makes it a lot harder to interpret. And the thing is, the night sky is constantly flickering. There's a lot of stuff that's dying, there's a lot of stuff that's erupting, and that means if you just see something turning on suddenly, and you don't know how far away it is, you don't know what it did. I mean, there's going to be 1,000 times more supernovae than neutron star mergers. So you really want to know that this is the thing you ought to be looking for. And that's why the sound is really nice. But yeah, we had a beautiful one 2 years ago, actually, that James Webb is allowing us to look at. So that's nice. A few every in the future.
Back there first.
How many more observations like this would you require to get a better precision on the estimate?
Of the Hubble concept, of the expansion of the universe? So, I want to emphasize, we're not sure that this is correct because you only have one object to calibrate against. But in theory, with 5 or 10 of these, you would know whether the supernovae was actually systematically off from the true value of the microwave background.
I have another question.
Yes.
Regarding the simulations, like I just want to get a very rough image. How do you do these simulations when you have to simulate such complicated physical laws with so many particles? I mean, of course,
Yeah.
you can simplify the laws, but still, I just can't get my head around how you run these simulations
Yes.
in reasonable times.
Yes. So, I guess the truth is that every person who does simulation is approximating some parts of the problem, and others are approximating other parts. If you want to really get down and do everything correctly, you should be modeling things at the level of a centimeter, even though the stars are at the level of 10 kilometers, and even though the thing they're throwing out is quickly at the velocity of many suns, right? So that's a very multi-scale problem. Computationally, you can do multi-scale if you just kind of scale down somehow, or you use microphysics on a small scale. So it depends upon which part you want to approximate. So the magnetic fields are famously difficult to do because those are happening on a very small scale. Most of what I've talked about today is actually the formation of the elements, which are, I guess, when you look at something like this, right, it's most of the elements are produced because stuff is thrown out, and that's a pretty large scale structure in some sense. It's also, there's this quirk that the neutron stars shine in a particle that isn't a photon but called a neutrino, and that little particle that, I mean, there's billions of them, trillions of them passing through every square centimeter of your body, but one will hit you in your lifetime typically because they are not very prone to interacting. You could put up a wall, a big beautiful wall, that's China, and you could make it a light year long, and a neutrino would statistically just pass through it, never noticing it was there. So those particles seem to be doing most of the heavy lifting, pushing stuff out, which makes it incredibly hard to kind of trust what you get from the simulations, because you need to understand that you trust a particle that you can't measure on Earth, which is what makes it intractable.
We have a question here.
If I may add to
Yes.
the simulations questions, what exactly the equations that you're trying to solve here? Is it Maxwell? Is it Newtonian Schrodinger?
I guess it's several things. So this thing here is kind of it's a nice GR problem. So its density is it has GR in it, but you're not thinking about the magnetic fields in this simulation at all, and that means you lose a lot of the complexity. Then there are other people who have to treat the magnetic fields, and then they're using something, a nice scheme for the maximality and stuff. In general, I guess it's very diverse.
Different based on what we were trying to simulate.
Yeah. And which part of the physics you wanna think is important.
I understand that neutron stars are like a huge collection of neutrons, but then how are the magnetic fields produced by them? Like do they have electrons?
Yeah, so they do have some. So the name is maybe a bit of a misnomer. So they're neutron stars because they're at the limit where neutrons don't want to be on top of each other. So the pressure that's holding them up is that there is a lot of neutrons in their core, and there's a lot of neutrons through the star where the pressure has been so big that protons and electrons, the normal constituents of charge in the universe, they bind together and you get a neutron. But there are still free electrons running around, especially on the surface. And one of the things that happens is that you're somewhat conserved in your magnetic field from the star to the neutron star, at least the total energy in the magnetic field. And the star was, what was it? It's like let's say 100,000 times bigger than the neutron star was in every one of the spatial dimensions. You condense that down to a tiny object and you get a huge magnetic field. Yeah. These are good questions.
Sorry.
Yeah, with that.
Yeah.
Okay. Just quickly, a huge magnetic field relative to the size of, or the space that the neutron star takes up. Do you mean, or is it bigger than the original star itself?
It would. I mean, the total energy in the magnetic field would be similar to the star itself. It's just the
Right.
density that's high. But the density is so high that atoms begin being these weird spaghetti things.
And sorry, I didn't quite understand the significance of your comment in the talk earlier where you were mentioning about magnetic fields with the neutron stars, but something different for black holes and
Yeah.
something around
Yeah, so the question, I guess, is so you have two things that are supposed to be the most magnetic things in the universe, and you form a black hole. And black holes are not characteristically thought of as somebody with a big magnetic field. They can't really conserve it, at least. But the question is, you have this thing that was once magnetic, becomes a black hole, and the black hole has to lose it at some time scale. The question is, what is that time scale, really, that you give that away? And I don't think there is a really clear answer to that. So the thing I was saying was basically, you can imagine, like when you have solar eruptions, you'll have some, magnetic fields on the surface of the sun that'll reconnect, and then it'll throw out matter at high velocities that'll maybe destroy a cable here on Earth or something. But if you do that with the most magnetic thing in the universe, you can really throw out quite a lot of matter. Yeah.
You have a question there?
Yeah, so Pauli's exclusion principle explains the formation of neutron stars, right?
Yes.
So does it play any role in how these two neutron stars merge, or is there any law which guides it? Or
So it's a very good question. So Pauli's exclusion principle. So there's several weird things here. One is the neutron, I think, was discovered in 1932, and the idea of the neutron star was suggested in 1933, which to me is wild. They discovered this new particle, and a year later they already had a star that they knew could be out there. So the Pauli exclusion principle is, it's saying something about how close we can put matter fundamentally in this quantum mechanical limit. The stars aren't really talking to each other in quantum mechanics, they're talking to each other in gravity. So everything they're doing, you can even do Newtonian. You can like write out the old equations by Newton. You wouldn't get the sound right, so you'd need some. It's kind of a little wish-washy, but you'll do the Einstein part of it, and then you get the two things merging. So you don't need to invoke quantum mechanics in the merger. What you get when they've merged, however, is a thing that's hot and quantum mechanical, and in 30 milliseconds it's going to be a black hole. And that's a kind of uncomfortable space to be in, because then you need quantum mechanics and the gravity. And maybe the magnetic fields at the same time.
Okay. Any more questions?
I assume you understood everything then?
If it's all right.
Oh yeah, sure. Yeah.
What's next for you personally from here on?
That's a sweet question. So I've enjoyed the last few months here in Japan. There's a professor in the department that me and Ken are working with, Kento Osaka. There's a lot of things in the universe that flicker. And I think surprisingly to me, we don't fundamentally understand how they behave. So right now I'm playing around with this. It's also two stars merging, but they're the size of the sun, or many suns big. And then, they collide into each other, and through this weird quirk of physics, they create this, okay, that's going to be hard to explain, but this super hot electron fluid moving out, and we can see this hot electron fluid, and I just think that's fun. The universe creates a lot of beautiful things, and we barely scratch the surface in these transient parts of the universe. But thank you.
Okay. Sure. Right here.
In our current understanding, I believe it's still like beyond our physics, but like when a black forms when two neutron stars collide, is there like one point where the black hole is created and it starts expanding, or does like the whole entire area suddenly in an instant becomes a black hole?
Yeah.
I just wonder how that process goes on.
One of the kind of weird things about black holes, they're kind of made outside in. So okay, I don't want to write on a blackboard here, but basically the statement is the size of a black hole, how should I say, the radius of a black hole just grows with its mass. And so if you make something twice as massive, you make it 8 times as big a volume. And that means once the two stars have actually moved close enough, the black hole doesn't form inside out, it forms from the biggest surface where you get enough mass within it to make a black hole. That's kind of quirky, I guess, because the inner part hasn't actually yet gotten to the black hole stage, because the outer part hasn't shrunk into it yet, but the outer part kind of recedes behind the horizon, it creates itself. It's also quirky enough because the radius goes as the mass. It means that when you go to the biggest black holes in the universe, their average density is tiny. So like M87, the black hole, the first one they took an image of, has a typical density lower than water, because it's so big that the radius it's expanding out to is actually almost nothing all the way. So if you made something which was just a big bathtub but the size of M87, you instantly get a black hole at the surface, but not at the center. Which is weird.
Those things were understood through simulations or by like I don't know by actual observations.
You've never observed the inside of a black hole, so it's extending the laws of physics in a regime where we know they break down, which is also slightly problematic, but it's the best version we have, I think.
Jace, you have a question?
Yeah, I have a question about black holes. So, when light and matter enter a black hole, is it just gone? Like there's no escape. So, like the scientific theory that matter and energy can't be destroyed, does that apply with black holes?
Yes, it does. I mean, it's not destroyed just because it's behind the black hole. It's just hidden from us. So the total energy of the universe can be conserved in some sense. So the information is actually what people normally call it in black holes. It just means that at some point the curtain is pulled and you don't get to that part of the universe again. It doesn't mean that that part of the universe doesn't exist. It just doesn't really communicate with us anymore. One of the big problems with black holes is actually that Hawking in '73 suggested that they could evaporate, which means they can disappear, which makes this into quite a big problem because you can make a black hole out of something, out of us, out of all our memories. And quantum mechanics is very explicit that you don't actually ever lose information. And then you can make a black hole, conceal all the information at the center of the black hole, and then you can evaporate the black hole and destroy it. And at that point you've invented a machine that can, in theory, destroy anything, and in theory destroy the universe. So on a really large time scale, that becomes a problem because we're all going to end up, well, at least dragons, many body systems in the Milky Way, we end up in the middle of the Milky Way, we end up in the black hole, we become part of that thing, that black hole maybe evaporates on an absurd timescale, and then we disappeared, and the universe kind of disappeared, which is kind of unfortunate. But it's not clear that Hawking is right, by the way. Again, that's a scientific debate, we're still trying to figure it out, but that's very much within the laws of physics, or laws of mathematics more than the laws of physics, so we're kind of discussing.
Okay, so unless there's any last questions, yes, we can thank Albert again. Okay, so I'm just going to go through a few advertisements and announcements at the end here. Okay, so for those of you who are new, we are Space Cafe Tokyo. We do an event here almost every month, always at the same location here at Good Heavens. Good Heavens, please follow them on social media. They've been hosting us for a very long time. We have a good partnership with them, and they do a lot of events here. So not just Space Cafe, but check out their Facebook or Instagram for upcoming events, and I'll just mention a few in the next month or so here. So on this Thursday, they have an event, Beers for Books. You might have noticed there's a lot of books here that are all for sale, and apparently that's going to be an event combining two very interesting topics. Next Monday is Mods Night. Isaka, what is Mods Night? Music.
Mostly music.
Okay. So they have a lot of music events here. And if you're interested in, I think they had, who did you have last month? You had someone pretty big, right?
What? Who? Comedian?
Oh, okay, sorry, that was a comedy event. Okay, sorry, I mixed up my my events. But so next Monday they have a music event here. On Sunday, May 4th, they have charity quiz night. Friday, May 9th, they have Half and Friends meetup event. And then they have International Comedy Nights, Victor Petroskin on Wednesday the 28th, Friday the 30th, and also June 4th. So that's just a list of some upcoming events here at Good Heavens. So you can find all of this information on their social media. Okay, so this is a kind of a fun announcement for me. So our former, the text kind of got clipped there, but one of our former Space Cafe speakers, Hippo, is a friend of mine. We've been good friends for many years, and he actually wrote a children's book, a space-themed children's book, that is coming out this Friday on Amazon. And it's called Yota's Star, or Yota no Hoshi in Japanese. There will be an English version soon. and there will be a paper version soon. But right now it's just on Kindle. So this was written primarily by Hippo, but also a big team of artists, and myself, I contributed to it as well. So please follow our group, UArt, from this Instagram link, and you can pre-order on Amazon using this QR code here. And we'll try to have him give a talk at some point, possibly with a collaboration event we'll announce at some point, about the process of writing this book. So, okay, so we also want to advertise our friends at ReadCan. They have a blog called It Ain't Magic. This is where they discuss various science topics, particularly ones that they are working on over at ReadCan. So a lot of them sometimes come to our events, and we try to promote their blog. So please check out either on their social media. They also have a website which you can see. Unfortunately, that got cut off there. But their QR code, you can get to their blog on the internet. Next month, we also want to advertise Nerd Nights. These are our partners over at Sugamo, and they do an event every month also. They have 2 speakers every month talking about various topics, and next month is going to be on Friday, May 23rd. So their speakers are going to be talking about detecting fabricated cognitive deficits and concealed knowledge related to criminal activity. And another speaker is going to be doing a tour of @Proto, the open protocol behind Blue Sky. So if you're interested in that, check them out at Sugamo at Ryozan Park Lounge on Friday the 23rd of May, and you can find them on social media here. So our next event will be next month, May. We're still finalizing the details, so please check us out on social media to hear the announcement of the next date. So if you haven't done so yet, please sign in using the QR code here, and those are our social media links, so follow us to find out about future events. And we also have a YouTube channel where you can see this talk again and some previous talks. And just the Space Cafe Tokyo team, so I'm Ken, that's Mayuko by the door, Talina over there, and Chase taking our photos and video. And if you'd like to stay, interact with Albert or anybody else in the audience, please buy another drink, buy some food to support the bar. And